Hello, good evening, my dear lovely lions, my warriors, to the Vedantu NEET English channel. And this is your Captain Shreyas, your Capto, your physics master teacher, who has been guiding and training kids for more than 12 years, guys. And here we are on this channel. Make sure that you are liking the video and also subscribing to the Vedantu NEET English channel, the #1 channel for NEET English in the country. So today, we are already on chapter number 3. The current electricity chapter. Make sure that you attend all the NCERT line by line series. This will not only help in your board exams, but obviously NTA is going to pick up NCERT. They are going to go through the text and make the questions from NCERT. So make sure that you know every important line and every single example from NCERT. Hi Krishna, hi Jasmine, welcome Atluru, nice to see you back. Hi Mardale. Hello Sumati, welcome aboard. Nice to see that fire in the chat box. Awesome, super duper. Hi Soumya, good evening. I hope you guys had your dinner and are full of energy. I know sleep will come in the May, but we are not going to give up. We are NEET warriors, we are future doctors, so we have to fight it. We will struggle, we will win this war of NEET 2025. Okay, so stay with me till the end. I hope you have marked your attendance. If you have not marked it, do that and smash the like button right away, right now. And also do not forget to check out this particular scholarship link for all of you. MVSAT examination is nearby. I hope you are preparing really well. The link is there down in the description box below. The biggest scholarship exam where more than 2 lakh students are going to give it, and you too can get your national level ranking. And just for participating, you will get free study material and also chances of getting scholarship. And even if you are enrolled in a course already, so you can get that refund amount because of this particular scholarship, right? So a lot of prizes to be won, a lot of goodies to be given, offline as well as online. The dates are mentioned, syllabus, everything. I have already cleared it out in a live class. So make sure you're registering by entering your mobile number right over here, so that you know when the test is and you are preparing for it. That will be your first step towards NEET 2025 or 26. And if you have your friends who are not yet, enrolled in the test, encourage them to give MVSAT. Cool? Thank you guys for all the fire. Really, I feel really warm looking at all your chats. Thank you so much. Thank you so much, Satya Sri Krishna. Thank you so much, Soumya. Hi, VS Vetri. Present. Glad. So, in this chapter of current electricity, it starts off with basic current parameters like density, drift speed, relaxation time, resistivity, resistance, EMF, all these things. Then slowly we move on from those to circuit problems, where you talk about batteries in combination, resistors in some combination, Wheatstone's bridge, and the power. So that is the basic flow of the chapter. If you remember little bit from your 10th standard, I hope you, probably, I don't know, maybe it has been a while. This is a much better extension of that chapter, which you might have studied back in 10th grade. All right. So, so this introduction part is just about telling you how current electricity is there everywhere. I mean, they talk about natural situations like lightning, as well as, a artificial man-made situation like a torch. So if you talk about your fans, your AC, your light, your torch, your computer, your mobile, all of them work on the principle of current electricity. And naturally occurring phenomena are like lightning. So when lightning occurs, current, basically flow of charges happens from the clouds to the earth. So that is naturally occurring current. And if you ever wondered what a current is like a river, that's what they say. But a river which is, instead of carrying water, it is carrying charges. So a river which is like carrying charges, is that phenomena is being called as the current. Now we know that river will flow through a path. Same way the current will also flow through a path which is a conducting path, or else we wouldn't be able to survive or live. Just imagine somebody turns on the light, but instead of the current going inside the bulb, it flows through our body. It doesn't, because there is air, there is some insulation, rubber, wood, so many non-conducting materials are there, so which stops the flow of current, and it only allows the current in a certain path, which is the wire, which is a conductor. So that is what the basic introduction is. That's not so great or important. So just to build up the mood, like warming up, just like you guys warm up the chat box by putting those fire emojis. Hello, KV Thamis. Hi, Scientists of India. Welcome, welcome. Hi, Prasant. Yep. Now, the main things start from here, which is basically the electric current. Imagine a small area which is held normal to the flow. Both the positive and negative charges may flow forward, backward. In some intervals, some charges move this way, some charges move that way. And you might see that the total charge which flows is this much. Then the current is given by Q by T, which is defined to be the current across the area in the forward direction. If it turns out to be negative number, it implies the current is in the backward direction. Now the main things which you need to highlight over here is basically this, and is defined to be the current across the area in the forward direction. The net amount of charge flowing in the area forward direction in that time interval t is basically this much. Then this is the value. Okay, now I'll explain you what this means. Say for example, there is a positive charge. It goes like this and it goes like that through some maybe cross-sectional area. Maybe through some cross-sectional area over here. So if that particular charge was, let's say, Q, and this moved in a time of t, then I will say that the current is flowing. I will say that the current is flowing in this direction, in the direction of the positive charge, and the value of the current is basically Q by T. I will say that the value of the current is the charge which flows in a unit time. Now just imagine the same cross section, but this time what happens is you have instead a negative charge. You have instead a negative charge, negative Q, which goes through that particular cross section in a time of t. Now if you ask me what is the current will still be Q by T, but it won't be here. Current is always assumed in the direction of the positive charges. Here negative charge goes this way. It is same as saying if evil is going out of me, I am becoming better. If good is coming into me, I am becoming still better. I hope you understand both of them are creating the same kind of effect. If something good is coming into me, I am becoming a good person. If evil is going out of me, you might say, sir, something is going out of you. But it's okay. It's the evil which is going out of me. Still it is making me into a better person. So same way, if negative charges go here, is the same as saying the positivity is going on this side. Hence, the current will still be charged by time only, Q by T, but the direction will be here. Is that making absolute sense to all of you? Same way. Now, just imagine there is this cross section, and what happens is there are two positive charges which go like this through that particular cross section, okay, and there is one negative charge which basically goes through the cross section like this. You might be like, sir, this is combination of multiple charges. Now what is the current exactly? I'll tell you. These two charges going here will make the total charge going this side Q plus Q. This charge going here is same as saying a positive charge going this way. This is same as saying a positive charge going the left way. So actually the charge is not going right side, it is going left side. So I will put minus Q and this whole thing divided by time. Let's say there was one more charge over here which was going this way, then I would have put one more Q over here. So this will be the total current. So in this case, it will be 3Q minus Q, which is 2Q divided by T. Is that okay, my dear students? How this works? And then what if this is the scenario? Let's see if you guys can figure this out. But before that, the direction of the current in this scenario, was here. This was the direction of the current. Come on, my dear students, I want everyone to answer this. there are two positive charges which are going like this, and there are two negative charges which are basically going like this. There is one negative charge which is going like this. Okay, so tell me, in this particular scenario, let's say there will be three charges. Now tell me, in this particular scenario, what is the total current in the circuit? What is the total current in the circuit? So if you notice over here, three charges, positive charges, are going towards the right hand side. So Q and Q and Q charges went to the right hand side. These negative charges going right is same as saying two positive charges went to the left. Two positive charges, it's same as saying two positive charges went towards the left. These two negative charges going towards the left is same as saying two positive charges went to the right. So won't these two end up cancelling out each other? Won't they end up cancelling out each other? That's it. The whole thing divided by time is the current. So these two cancelled. The positive charges went here. Hence the current in this scenario is towards the right hand side. So this is exactly what has been explained in this paragraph. So this formula might look simple, but you should know how to exactly apply it. Through these examples, I hope you have understood how this formula has to be applied or how you will actually use these things. Is this absolutely clear? Finally, yep. All right. Very good. Very good. Awesomeness. Awesomeness. Now, in the next part after this, okay, but before going ahead, they also tell you one more thing. Let's say I tell you that the current in this is 2 units, and I show the arrow mark like this. And there is another diagram where I show the current is like this, and the current I will say it is -3 units. What is the difference in these two? The difference in these two is, see, when I say the current is +2 and I show the arrow mark, means the positivity is going like this. The positivity is going like this. Or I can say alternatively, the negative charges are going like this. That is what it means. And the answer being positive tells whatever I have assumed is correct. If something is positive, that means whatever I assume is correct. But here it is negative, means whatever I assumed is wrong. So actually charges are not going here. So the charges positively are going here, or same as saying the negative charges are going this way. That is the meaning of negative value of the current. Don't get scared thinking, sir, current became negative, am I wrong? No, that's what they say. If the current is negative, then it just means the current is in the backward direction. So that is what they just say over here. So another important point over here, if it turns out to be negative number, it implies the current is in the opposite direction or the backward direction. That is what I have explained. Now the next part talks about the derivative of the charge with respect to time, and they have given one formula over here which is the same as dq by dt. And why they have given this is because current need not always be steady and it may increase and decrease. Sometimes more current goes, sometimes less current goes. Everybody might have turned on the fan and be like, oh sir, it is very hot, increase the fan, more current will come. The AC is not making me cold enough, make the AC speed fast. So you will make the AC stronger to blow more cold air. So it will take in more current. Or sometimes you are feeling very cold, you reduce the AC. So current can change with time. And when current changes with time, the charge which is going through it is also changing at different rates. Sometimes more charge, sometimes less charge, sometimes constant charge, sometimes again more charge, and even more charge, and again even less charge. So the rate at which the charge flows can change with time. So that is why you write it in the derivative form, which is the rate of flow of charge. And the unit of current also has been defined right over here. The unit of current is basically ampere, and ampere is nothing but how much charge flows per unit time. It is a coulomb of charge which goes in 1 second. So remember this, 1 ampere is nothing but 1 coulomb, which goes in 1 second. Now this is a very informal definition. The formal definition comes in magnetism chapter. You will see why later on, but don't worry about it. Okay. Now, if you ask me how big is an ampere, let me tell you, your mobile phone when charging takes few milliamperes of current. Yes, milliamperes. The AC, the heater, your kettle, water kettle, all those things takes a few amperes, like 2 amperes, 3 amperes, 5 amperes, or even up to 10 to 15 amperes, not more than that. But lightning, which strikes the earth, which is very dangerous, that is thousands of amperes. That is why it is considered to be very, very dangerous. Got it? So a charger typically in milliamperes, your laptops milliamperes, but you know, heaters and all of that go in amperes, and lightnings in thousands of amperes. That is what you should understand, the scale of ampere. Now to give you an example of this, just say, for example, these kind of questions have been asked in the NEET previous year papers. They give you charge is equal to, let's say, t cube minus 2 t square plus 5 coulomb. Question will be, find the current at time is equal to 1 second. This kind of question can come. So what you will do, you will see the given information and realize, oh, the charge is changing with time. To find current, I have to differentiate it. I have to take the derivative of this, dq by dt. Okay, no issues. Current is nothing but derivative of the charge, which means I have to take the derivative of this entire thing, t cube minus 2t square plus 5. What might be the derivative of t raised to 3? 3 comes here, power reduces by 1, so it will become 2. Minus 2 will come as it is a number. T square's derivative, 2 will come outside, times power will reduce by 1. 5 being a constant, the derivative is 0. So therefore, the current in general will become 3t square minus 2 2s are 4t. Now the question is at 1 second. So I1 will be, substitute the value of time as 1 minus 4 into 1. So what is the answer? 3 into 1 is 3 minus 4, which is minus 1 ampere. Now you will be scared, sir, I got the answer as negative, will I get negative marks? Don't be worried. You will see the options. If it says minus 1, you will just mark it. What does this minus sign indicate? It just indicates that whatever direction you had assumed is probably wrong. If you say this is the direction of current, actually the current is not that way, the current is going this way, having a magnitude of 1 ampere. That is what it means. Is that clear, everyone? Very good, Krishna. VS, Madhumati, excellente. Suganya, long time, I am very good. Suganya, yes, I was not able to take the classes when I was back in Pune. I was meeting all lovely students, just like you. Yes, correct. Moving on to the next concept. Electrical currents in conductors. Electric charge will experience force. Okay. Now in this entire paragraph, I'll tell you what they have exactly done. So there are many lines in this section, entire section 3.3 before 3.4 going to Ohm's law. This entire section is talking about how exactly the charges move and what exactly conductors do in helping the current flow. Let's just go through it. Let's just read through it, okay, calmly, and then we will understand it. Okay, first let's read calmly. Don't worry whether I'm understanding or not, forget it. Let's just read through it. So when a charge will experience a force when an electric field is applied, if it is free to move, it will move in contributing the current. In nature, free charge particles exist like atmospheric strata, the ionosphere. However, atoms and molecules, the negative charges, which are basically the electrons, and the positive charges, which are the nuclei, are bound to each other. Hence, they are not free to move. Bulk matter is made up of many molecules. In fact, a gram of water itself has so many molecules. Now, these molecules are packed and the electrons are no longer attached to the individual nuclei. In fact, in some of the materials, the electrons will still be bound and they will not accelerate even if you apply a field. In some materials like metals, these electrons are practically free to move, and they will move inside the conductor when electric field is applied. If you consider solid conductors, then of course the atoms are tightly bound to each other, so the current is carried by the negative charge electrons. And there are, however, other types of conductors like electrolytic solutions where both can move. In our discussions, we only focus on solid conductors. Consider the first case when no field is present. Okay, before going here, let me just start underlining few things. An electric charge will experience force if an electric field is applied. If it is free to move, it will contribute to the current. Okay. In some materials, the electrons will be bound. They will not accelerate even if the field is applied. Whereas in other materials, notably metals, some of the electrons are practically free to move within the bulk material. These materials are basically called conductors, and they develop electric current when electric field is applied. Okay. Okay. So that the current is carried by the negatively charged electrons. Okay. We only focus on our solid conductors. Okay. Consider the first case when no electric field is present and the electrons will be moving to the thermal motion, will collide with the fixed ions. An electron colliding with other ion emerges with the same speed as before the collision. However, the direction of the velocity is random. At a given time, there is no preferable direction of the velocities. Thus, on an average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So there will be no net current. This is considering the first case when there is no electric field present and they will be moving due to the thermal motion. Okay. I will just read it and then I'll explain. Don't worry. Let us now see what happens to such a piece of conductor when field is applied. When electric field is applied. This is the next case when electric field is applied. Okay. Now you take a section and you see that some positive charge which is distributed on one disc, negative charge on the other disc. We attach the two discs on flat surface of the cylinder. Electric field will be created in the direction from positive to the negative charge. The electrons will be accelerated. Okay, they will thus be moving to neutralize the charges. The electrons, as long as they are moving, will constitute electric current. Hence, in the situation considered, there will be current for a very short duration and not after much time. We can also imagine, see guys, NCERT will try to complicate things, but wait a minute, Shreyas Sir is going to decode this entire NCERT for you. We can also imagine a mechanism where the ends of the cylinder are supplied with fresh charges so that, continuous flow is there. In that case, there will be a steady electric field in the body. Okay, so imagine where ends of a cylinder are supplied with fresh charges to make up for any charges neutralized, so that in that case, there will be a steady electric field in the body. And this will result in continuous current. This will result in continuous current rather than a short current. This mechanism by which you make a steady current is basically called as cells or battery. They are called as cells and battery. We shall study them later. All right. So what is all of this? Let's decode. Imagine there is a house. Imagine there is a house. This house, okay. This house is basically the nucleus. This house is the nucleus, which is basically positively charged. In that house, there are many kids, maybe 4 or 5 kids. Okay, these kids which are there, these tiny mini pandus which are there, okay, these kids are basically negative charges, basically the electrons. Now just imagine, maybe your favorite hero or heroine has come. Maybe Thalapathy Vijay came in the neighborhood that way. Or maybe Dhoni came, okay, near your house, maybe in a coffee shop for some reason. Or maybe some beautiful actress came, okay. So what will happen is these kids are like, I want to go out of the house. I want to go to the house. I want to meet Dhoni. I want to meet this person. My favorite hero, heroine has come. They will try to go, but the parents will be like, no, you can't go. You have to stay in the house. So usually in an atom, the electrons are bound. They cannot go outside this door. Agree or disagree? But inside the house, they can keep moving randomly. They are running around like mad people. They're running around like mad people inside the house. That random motion happens within the bounds of that vicinity of that atom, but not far away from the house or that atom itself. That random motion of the electrons is associated with the temperature or the thermal energy. So when you take, let's say, copper or gold or aluminum, inside that so many electrons are there and they are moving randomly here and there, they're colliding. That random motion is associated with temperature. If you heat it up, there is more randomness. Imagine there is more heat in this. These kids are running around like crazy. They are going nuts. They are going mad. Is that clear? Okay. Now imagine many such houses. Imagine many such houses. Obviously, with houses come many such kids out here. Many such kids. If, for example, our beautiful Champa has come, all these Pandus are at home. Okay, this is a beautiful Champa. All these kids are like, all these Pandus are like, I want to meet my hero, I want to meet my heroine, I want to meet my superstar. These houses are not letting them go. This Champa, this superstar is like that external field. What is that Champa or that external superstar? Like the field, electric field. What does electric field do? Electric field applies force on the electrons. Is that right? Force on the electrons. So now what happens is, if it's a non-conductor, basically an insulator like rubber, wood, paper, marble, stone, soil, bad conductors, no matter which superstar comes, no matter which Champa comes, these electrons can never leave their houses. The kids will be crying, but they can't leave. So, for non-conductors like rubber, etc., the electrons can't leave the atoms. They cannot flow even if there is an electric field, because of which they do not conduct electricity. But in a conductor, the parents are little lenient. Okay, your superstar has come, go. Here, take some money, okay, enjoy, okay, eat something, okay, maybe drink some juice, okay, here, have some chips. So the parents gave some money, okay, go, meet your superstar. So these kids run and meet the superstar. So there is a flow of charges. These electrons flow. So there is a flow of charges because of an external influence. And that's what constitutes current. Where does it happen? In conductors. Example, metals, copper, silver, gold, aluminium, iron. So all these substances, you will see the parents of their houses, basically the nucleus. The nucleus is lenient and they have let the electrons free to roam around. Now, if few of the kids meet the superstar, the other kids will think, "Arey, already this superstar is surrounded with so many kids over here. What will I go and do?" They will get demotivated. Already this Champa is giving bhav, is giving, importance to the few Pandus around whatever that star. So the other kids are like, okay, my role is not there. It's okay, Papa, I will stay at home. It's okay, Mom, here, take this money. I'm going to stay at home. So the other kids do not have motivation. But imagine one more Champa comes. One more Champa comes over here. One more superstar comes. Then the next few kids will get motivation and they will go towards the Champa. Is that right? But then again, other kids will be like, okay, already the Champa is surrounded by Pandus. I will not do anything. Then you need one more Champa. Imagine there is a continuous supply of Champa. Imagine there is a continuous supply of Champa. What will happen? Kids will keep coming. Kids will keep coming. Got it, my dear warriors? So, what they explain in the paragraph is that if you apply the electric field using, some plates or anything, then the charges will get attracted and then the charges are neutralized. After that, there is no current. But if you constantly maintain the electric field, if you constantly maintain the supply of electric field, how do you do that? By connecting a battery, a cell. then charges always have that motivation because of that electric field to leave the nucleus. They are free and they continuously flow inside the conductor, and that's how current gets established. Is that absolutely clear what they have explained in these 3-4 ridiculous pages or paragraphs? I have marked all the important lines for all of you. This is the main thing what they have explained. Clear? Have you understood it? Are you able to visualize this now? What happens inside a conductor? Electrons, they want to leave, but they can't leave for a non-conductor like rubber or wood. But for conductor, they can leave, free to move. Once they move, the charges get neutralized. Then there is no motivation for the new electrons. So the current will be only for a short duration. So to continuously maintain the current, you need to continuously give the electric field. That external motivation has to be there. So that comes through a battery, a cell. You buy those cells, you connect it across a wire, continuous electricity flows. Okay, clear? Awesome. Yes, pakka clear. Very good. Now let's come to basic Ohm's law. So now that we have understood what current is, Ohm's law is a law which was given almost like 200 years back, guys. Okay, and he said that whenever he applied whenever he connected a battery or a cell across different devices and he changed the battery's voltage or he increased the power supply, he found that the current was proportional to that voltage, and that is exactly what Ohm's law is all about. So a conductor through which current I is flowing and voltage V is the voltage difference between the ends of the conductor, then Ohm's law says voltage is proportional to the current, or the constant of proportionality. The constant of proportionality is basically called R, which is the resistance. How much does it resist the flow of the current? The unit of resistance, the SI unit of resistance is basically Ohm and is denoted by the symbol this sigma over here. The resistance not only depends on the material but also the lengths, the breadths, everything, and we will see how it is determined in the next slide. So basically what Ohm said is that if you have some device and he passed different values of current, so he sees what is the current and he also notices what is the voltage difference across the ends. First he saw when there is 0 volts, then there is 2 volts, then let's say there is 4 volts, okay, then let's say there is 10 volts. The currents that he saw, for example, no current over here, then let's say there is 0.5 current over here, then he saw basically 1 ampere current over here, okay, so then he saw basically 2.5 ampere current over here. He saw that the current is directly proportional to the voltage. And if you notice over here, if I write V is equal to I multiplied by R, take any value, for example, I take the value of 2, okay, is equal to current is nothing but 0.5 multiplied by the resistance. I will get the resistance as 2 by 0.5, which is 4 ohm, which is basically 4 ohm. So this tells me the resistance of this device is 4 ohms. If the resistance was more, then this won't be the current would be less. If the resistance is less, for the same voltage, there would be more current which would be flowing. That is exactly what Ohm said. Yep. All right. Very good. Now, this is only true for something called as ohmic devices. Ohmic devices, you will see later on in semiconductor chapter that there are non-ohmic devices as well which do not obey Ohm's law, which means if you increase the voltage, current increases but not proportionately. Suddenly there is a sudden jump, then it is not increasing so much. So that weird behavior can happen. At that time, imagine this happened in 1828, the knowledge of semiconductors was not there, so he gave the law, although this law is only valid for mainly conductors, not for semiconductors. Is that absolutely clear, everyone? Adesh, obviously JEE Mains is tougher, but board is tough if you do not understand the concepts. Yeah. Now, how does it depend on the dimensions of the how does the resistance depend on the material as well as the dimensions? So we'll come to that as well. So the resistance depends on material of the conductor as well as the dimensions of the conductor. How does it depend? That is what they have explained in these few paragraphs right over here. Now, what they have written down in these two paragraphs, I will just have a look at it, okay, and I'll explain and decode it for you. So first they take a single slab of conductor of certain length and area, then they increase the slab's length, and what happens is basically they put another slab along with it to increase the length, and they apply the same voltage. They find that the current has become less. That's because the resistances have become more, okay. So they conclude from here that the resistance is proportional to the length, and next time, instead of placing one slab after other, they cut the slabs or place it besides each other. Then they find that the resistance has increased, and then they conclude that okay, resistance is inversely proportional to the area. So how they are doing this, let me tell you. Imagine this is the conductor. Imagine this is the conductor, and what they do is they have passed in some current over here because there is some voltage difference. So they find out what is the resistance, and the resistance comes out to be, let's say, V by I, because V is equal to IR, R will be V by I. Next time what they do, they take the same conductor, but they put another similar conductor in front of it so that the length becomes basically double. So now the length is double, or you can think as if there are two conductors side by side. What they find is, if they apply the same voltage now across this, the current which passes through this becomes I by 2. The current which passes through this will become I by 2. So this resistance, this new resistance will be voltage by current. So it will be V by I multiplied by 2, but V by I is nothing but R. So it will become 2 times of R. So the new resistance has become 2 times, and the new length was twice the old length. From this, what they concluded, resistance is directly proportional to the length of the conductor. Longer the conductor, more is the resistance. Is that absolutely clear, everyone? How they were able to conclude this? By putting another conductor, and if you put 3 conductors, the resistance will become 3 times. The current will become 1/3. If you put 4 conductors, resistance will become 4 times, one after the other. Now, they did the same experiment, but this time they put another conductor besides it, another identical conductor besides it. So instead of one after the other, they put another identical conductor besides it like this, and they applied the same voltage, say for example, the same voltage like this. What they found was, now the current had 2 paths to go like this. In fact, the current became 2I. The current became double. So from this, if you find what is the new resistance, voltage is V, current is basically 2I. So it will be half into V by I. V by I is R, so it will be R by 2. So what they found is the resistance has become half when the area is 2 times the old area. From this, they concluded resistance is inversely proportional to area. Area doubles, resistance becomes half. Exactly. So that is how they were able to finally write down. Okay, resistance is proportional to length, resistance is inversely proportional to area. Therefore, resistance is proportional to L by A. Therefore, I need a constant of proportionality. Instead of proportionality, I put a symbol called rho. What is this rho? This rho is that constant which is called as resistivity. Resistivity. Understand that. So this is called as the resistivity. This is resistance. This is resistivity. Resistivity is of a material. Aluminium will have some resistivity. Copper will have some resistivity. No matter where you find the copper, copper will have the same resistivity. But resistance depends on resistivity, length and area. If you take more copper, the resistance might be more or less depending on whether area is more or length is more. But resistivity is a material specific property. If I take a long rod of copper, then the resistance will be more, but resistivity will still be the same. If I take a wide copper, maybe the resistance will go down, but resistivity will still remain the same. That is what they have written down right over here. So this is a very, very important formula, guys. R is equal to rho L by A, and this constant of proportionality rho depends on the material, like I said, whether it is copper, aluminum, etc. of the conductor, and very, very important, not on the dimensions. And this rho is basically called as resistivity. Okay, that is what it is. So if you write Ohm's law, instead of V is equal to IR, you can write R as rho L by A. So it will become I rho L by A. That is what they have done. This is not so important. If you know this and Ohm's law, it's more than enough. Till this point clear? Very good, Atluru, Krishna, Madhumati, Chitra, Sukanya, understood? Clear? Shall we move ahead, my dear students? Everyone? Okay. Cool. Now they derive another expression called E is equal to rho J, and there is a very funny way they do it. See, V is equal to current into resistance, correct? What if I write resistance as rho L by A, and then they write current by area separately, okay, rho over here, and then that length they take it over here. Voltage per unit length, what is it? dV by dr. It is nothing but electric field. If you remember this definition which we have learned before, electric field was negative dV by dr. So here we are just concerned about the magnitudes, don't worry about the minus sign. Rate of change of voltage with distance, so voltage per unit length gives me the magnitude of the electric field. What is this current per unit area telling me? This is telling me, listen, if you have a cross section, okay, and in that cross section, for example, some current is flowing through it versus the same current flows through a larger cross section. Here the current per unit area is more, here the current per unit area is less. So I get a term called as current density. So the current is more dense, more current density in this case, versus there is low density of current in this case, because the area is more for the same current. So this current per unit area is given a symbol J. So remember, this J is current density, which is I by A, guys, which is nothing but I by A. Very, very important. So that is how they get electric field is J rho. Electric field is nothing but J rho. That is what they have got right over here. So you might be wondering, sir, what is this electric field that we are talking about? This electric field is the electric field inside the conductor, which causes the free charges to move. Very, very important. Without this electric field, remember this electric field is like that champa or that superstar giving that motivation for those electrons to move. So that electric field is inside the conductor which causes the motion of the charges. J, like I have told you before, is nothing but your current density. This current density will have a unit of ampere per meter square. How many amperes is going per unit area? That is nothing but your current density. Now this equation was completely in magnitudes, like you see the minus sign, everything was ignored, but actually it can be written down in the vector form. Now current density is actually a vector quantity, and you can rephrase this as J vector is your, or rather electric field vector is your J vector into rho, and then they define another quantity called as conductivity. Okay, so we'll come to that, but before that let's block all the important statements over here, and they write sigma is 1 by rho, which is nothing but called as conductivity. Okay, and they have also defined the current density vector over here. The current density which you have defined, the current through the unit area normally to the current is also directed along E. It is a vector. It is a vector. Okay. So now what have they basically told over here? Let me tell you. See, understand this. Okay, very carefully. Observe. This was our area. This was our area. Let's say the current flowing through it was like this. The current flowing through it was like this. The current value was I. Current density is a vector which is perpendicular to that area in the direction of that current. Okay, and it is a vector in this direction of the current itself. It is in the direction of the current itself. So that's how it has been defined. Now, if you talk about the conductor, if you look at the conductor, this, let's say, is our conductor. Inside the conductor, who moves? Which charge moves? Positive or negative? Nucleus does not move. Electrons move. Which direction do they move? Which direction do they move? Think about it. Which direction do they move? Yes, they move opposite to the direction of the current. These electrons obviously move opposite to the direction of the current. This is how the motion of the electrons is. And that is the reason why the current was in this direction. Okay, that is how the current was here. So actually the electrons are moving in the opposite direction. So in which direction the electric field is applying the force? Obviously, the force applied by the electric field on the electrons is in this direction. Hence, the electric field itself must be in this direction, because electric field on a negative charge applies a force in the opposite direction. So hence electric field was in this direction. So can you see electric field vector is basically parallel to the current density vector, is parallel to the current density vector. So that is why this equation which we had, E is equal to rho J. Rho was your resistivity. Okay. It can be written down in vector form also, because the directions are same for J vector and E vector. If I put J bar here, there is no harm in putting E bar over here. It's fine. It's perfectly fine. Got it, everyone? Why I am able to put the bar over here? Because electric field is parallel to the J vector. Now what they do in the next step is they take this E bar and this rho which is there, they just put it over here. and they get J bar. This 1 by resistivity, 1 by resistivity, they are calling it conductivity. So conductivity is 1 by resistivity. Meaning, if something is more conductive, it will have less resistivity. If something has more resistivity, it will have less conductivity. So they are just inversely proportional to each other. That's all. If somebody is less bad, that means he is more good. If somebody is more good, that means he is less bad. So they are inversely proportional. So it's just a way of looking at it in a different way. So this is then called as sigma, which is conductivity. These people come over here as it is and is equated to J bar. Is that understood? How this expression comes? How this expression comes and what they mean over here? Absolutely clear, my dear warriors? Cool? Very good. If you have understood it till here. If you have understood it till here. Awesome. Awesome. Now let's go to 3.5, where they talk about drifting. They talk about drifting and then they have given some interesting paragraphs here, and okay, till here. Okay, these 3 pages. Let's have a look at it. Let's read it and obviously then let's decode it. Okay, cool. Let's start reading, guys. Start. An electron suffers collision with different things, but after collision it will emerge with the same speed in random direction. If you consider all the electrons, their average velocity will be 0. Very important line. All the electrons, their average velocity will be 0 since their directions are random. Very, very important. So if there are n electrons, the velocity of the ith electron at any given time is this, blah, blah, blah. So the average is 0. Okay. No need to by heart this. Consider now the situation when the electric field is applied, electrons will be accelerated by this particular formula. And then, if you take it for any particular electron, okay, the velocity after time t is given by kinematic equation. Final velocity is initial plus acceleration into time. Since, since starting with its last collision, it was accelerated with the acceleration given by for time t. The average velocity for the electrons at the time t is the average velocity of all the VTs, okay, the average blah blah blah, since immediately after any collision, direction of the velocity of an electron is completely random. The collision of the electrons do not occur at regular intervals but at random times. Let us denote tau, the average time between the successive collisions. Then over a time, some of the electrons would have spent more time than tau and some less. In other words, the time t will be less than t for some and more blah blah blah. Then the average value will be this, and this you will get something called as the drift velocity. In this last result is surprising. It tells us that electrons move with an average velocity which is independent of basically independent of time, although all electrons are accelerated. This is the phenomenon of drift and this is called as the drift velocity. Okay, so again, this particular formula of drift velocity, very, very important. It tells us that electrons move with an average velocity which is independent of time, and this is called as the drift velocity over here. Okay, so what is basically explained over here? Let's understand. If you look at the life of any electron, it goes like this: hits somewhere, hits somewhere, hits somewhere. This is inside that, solid. It is moving randomly over here. So there is random motion of the electron, In fact, if you look for a decent amount of time, let's say 1 minute or 2 minutes or maybe 30 seconds, you will see on an average, these electrons have 0 velocity. These electrons have 0 average velocity. So I can say the average velocity is basically 0 Because the displacement is 0 for a decent amount of time, for a for an time interval, for a time interval. If you look at it, on an average the velocity is 0. Okay. Now if it was a stationary electron and if somebody applied an electric field like this, that electron will experience a force in this direction, because of which it will end up accelerating, and that force will be nothing but the charge. Let's say the charge is E multiplied by the field, So hence now there will be acceleration, which is given by force by mass. So the acceleration will be force divided by mass. The force itself is capital E into small e, field into E. Because of which what will happen? The velocity will continuously what? Increase. After some time it will become 2 meters per second, then 10 meters per second, 20, 40, 100, 1000, 1 lakh, if the field is continuous. There is nothing to stop it. But inside a conductor, even when you apply the field, because you connect a battery or a cell, it does not continuously increase the speed. After some time, what happens is, this electron which was being accelerated, yes, the velocity might increase. Yes, the velocity might increase for some time, but it will collide. It will collide with something. It loses everything, and again it starts from rest, again increases the velocity, maybe for a longer time, and again now collide, and then again it starts increasing the velocity. Maybe the collision happens sooner here. Again it starts increasing the velocity. So if you see, it's like going inside the traffic. It's not on an expressway which is continuously accelerating. So it increases the speed, thump, okay, full, one tight slap it gets, again it accelerates, thump, slap it gets, stops. That slap corresponds to collision. Every time it collides, loses its velocity. Again it accelerates, again loses its velocity. So if you see, it is not continuously increasing the velocity. Rather, I would suggest that it is on an average going with some average velocity. It is going with some average velocity. It's basically getting drifted slowly, and all of this was happening because of the field which was pulling it, accelerating it, and the collision which was again bringing its velocity down. So this is basically called as the drift velocity. What is this called? This is called as the drift velocity. Did you understand what is the meaning of this word drift velocity, VD? Everybody till this point? Yep. Very good. Excellent. Now what they say is, see, if you look for only one atom, this final velocity is basically initial velocity plus acceleration into time. But if you look for many atoms, this final velocity on an average, which is initial velocity on an average plus acceleration into time on an average, this velocity after the collision is going to be 0 on an average. This velocity on average is going to be 0. This final velocity on an average, by which they keep on moving, that is basically your drift velocity, VD over here. Acceleration, we just figured it out right over here. It is E by m. It is nothing but E divided by m. This time, sometimes longer, sometimes even longer, sometimes shorter. It accelerates for more, less, depends. But on an average, if you take that time over here is called as tau, which is called as your relaxation time. Relaxation time. Relaxation time means it gets slapped, thup, again it accelerates, slapped, again it accelerates, thup, slap. So it is relaxing, one slap, now no slap, it is accelerating, thup. So that time on an average is called as relaxation time. Got it, my dear warriors? Clear? So that is how they get this expression Vd is equal to EE by m tau. Vd is equal to EE by m tau. Where did it go? EE by m tau. Sounds only so nice, no? To say EE by m tau. Vd is equal to EE by m tau. Okay? EE by m tau is equal to Vd. Vd is equal to EE by m tau. Maybe some jingle will be made. If somebody is a musician, you can make some nice music out of it. Vd is equal to EE by m tau. Cool? Understood? Oh? Clear? Oh? Vd is equal to EE by m tau. I feel like saying it again and again. It sounds so interesting. Vd is equal to EE by m tau. Great. Now, moving ahead. What have they done? Such nice paragraph they have written. Something and all they got. And don't worry about this. I'll explain you. They have not mentioned anything significant, but they have done some derivation in a very textual format. I will explain everything over here. And then they get current density in the form of relaxation time. Okay. How did they do it? See, I'll explain this before going ahead. Imagine you take a conductor of some area, some length, okay, and it has some amount of current. So basically some charges will go through this cross section from here to here in a time of delta t. And as they are moving with a velocity on an average of drift velocity. Okay. How long does this session take? As long as it takes to complete this. Okay. If needed, we'll break it down into parts, but okay, as long as it takes to complete this, guys. Okay. If needed, we'll break it into parts also. All right. All right. So now, my dear students, over here, okay, observe this carefully. In this small time interval, these charges cross this cross section. So can I say that the amount of charge flowing upon the time taken being the current, I can say that charge upon delta t is equal to I, rather Q is equal to I delta t. Q is equal to I delta t. This is one way of looking at the charge. Second way is, this conductor will have some free electrons per unit volume. If you take a good conductor, it will have many free electrons in 1 unit volume. If it's a very bad conductor, not so many free electrons per unit volume. So I define a number called as N, which is number of free electrons which are participating per unit volume. So can I say this N is equal to the total number of electrons upon the total volume. Now the total volume, can I say it is area multiplied by the length? Area multiplied by the length. Okay, perfect. Now what I will do is that I'll think if each electron has a charge E, the total charge which I was talking about, this Q, will be the number of electrons multiplied by each charge has a charge E. So this Q which was there inside, which flows through that conductor, will be number of charges into E. But what is that number of charges, which we can see right from here? It is nothing but NaL. NaL. So guys, Q is equal to NaLe. Q is equal to NaLe, Nali. So, but Q is also I delta T. Q is also I delta T. So therefore, I can write it as NaL and then E over here. Is that absolutely clear, my dear warriors? Everybody till this point clear? That is what they have done in this particular thing. Current into time on this side and NaLe. Now what they do later on is that instead of writing length, length they write it as speed into time. Speed multiplied by time. That's it. And here on the left hand side, you still have I delta T. You still have I delta T. So this length which is there, what they have done, this length which is there, they have written it down as speed multiplied by time. Length they have written it down as speed into time. So now what and all will get cancelled? What and all will get cancelled? Delta T and delta T got cancelled. That is what they do over here. Okay, they will basically cancel that delta T and delta T, and they bring down this particular area below the current, the rest of the things as it is, N, Vd and E. N is there, Vd is there and E is also there. What is I by A? It is nothing but J. What is drift speed? Drift speed, we just got it over here. It is EE by tau m or EE by m tau. Okay, E by m and the whole thing multiplied by tau. So EE by m, the whole thing multiplied by tau, and this E is as it is. So from this we get J is equal to N E square E by m and tau. That is the formula. Is this derivation clear now, how they got it? That's the derivation, guys. That is exactly what they have obtained right over here. Okay, that's all you should know. Okay, so I've explained this in a very simple manner. This is paragraph manner. You will not understand it if you read it also. Rather, I have tried to keep it as simple. I found the charge here. I also found the charge other way, and then I just equated from here and here. Okay, so at this particular step, I have equated it. Cool. Let's go ahead. Now, they also say that this is exactly Ohm's law if we identify the conductivity as this blah blah blah. So what they have done over here is this is J, and remember there was an equation. Where did it go? Okay, let me write it down over here. J is equal to NE square tau by m, NE square tau by m, NE square tau by m into E. But long time back we also wrote down J is equal to E multiplied by sigma. If you have forgotten where we wrote it down, right over here. J is equal to E multiplied by sigma. We wrote it down just some time back. So comparing these two, so just by purely comparing both of them, what do you get? Just by comparing both of them, sigma is equal to NE square tau by m. NE square tau by m. That is what they have also done. NE square tau by m. Clear? Okay. So that is what they have obtained. Shall we go ahead, my dear students? Shall we go ahead, my dear warriors? Ready? Cool. Okay. Great. Let's go ahead to some questions. Okay, there is a question over here. Now, how to solve this question? I will definitely help you out with it. So they say that there is a wire of some cross section, some current, and Each atom contributes 1 electron. Density is also given. Atomic mass is also given. Compare the drift speed, thermal speed, and speed of propagation of electric field at what causes. Okay, fine. Now see guys, over here, what and all values are given to me. I'll just write it down. First of all, I am given the area of cross section. Area of cross section is 1 into 10 to the power minus 7. So 10 to the power minus 7 meters square. Then current is 1.5 amperes. Current is 1.5 amperes. Then each copper atom contributes 1 electron. Okay, density is given as 9 into 10 to the power 3. Density is 9 into 10 to the power 3 kg per meter cube. Atomic mass number also they have given. How much is it? 63. So 63.5 grams are there per mole. Okay, that is what they are given. And what we have to find is basically the drift speed and other things. Before solving anything else, this third part, speed of the propagation of the electric field in the conductor. Yeah, sorry, the second part, which we can do very easily, this part. What is the speed at which the electric field moves inside anything? Electric field, guys. If you remember light is an electromagnetic wave. An electromagnetic wave or light travels at what speed? The speed of light. So electric field, magnetic field, if there is a charge, zoop, the information will travel, the field will travel everywhere at what speed? Speed of light. So this answer, the speed of propagation of the field along the conductor which causes the drift motion should be the speed of light. I think the answer should be mentioned as it is. Yes. Yes. The electric field travels exactly at the speed of light. Okay, which is nothing but 3 into 10 to the power 8 meters per second. So electric field travels at the speed of light. So that is that particular answer. That is that particular answer, and we have done this. Now let's go to the thermal speeds of the atoms versus the drift speed. So for the drift speed, I think I will need all this information. How do I do this? How do I solve for the drift speed? Think about it. I feel to find out the drift speed, what do I need? What do I need? There is a beautiful equation actually. Which comes down as current is equal to NVDR. This equation, although it is not there in NCERT, please remember it. It will help you and it will solve the problems in a much simpler manner. So remember this formula. So because of which drift speed will be current multiplied by NEA. Now you will be like, sir, what is the value of the current? The value of the current is nothing but 1.5 ampere. Okay. What is the value of E? It is 1.6 10 to the power minus 19. What is the value of A, sir? Area is basically 10 to the power minus 7. What is this small n, sir? It is not given to you. That value is basically not given to you. So how do I find this small n becomes the next challenging part. This is number of free charges per unit volume. Since it was mentioned each atom contributes 1 electron, can I say it is basically the number of atoms upon the volume. Now volume can be written down as mass. See, mass by volume is density. So volume is nothing but density divided by mass. So mass goes on the top. Density is mass by volume. So volume becomes mass divided by density. Sorry, I think I missed this. I wrote it perfectly, no? Density is mass by volume, so volume will be mass by density. I wrote it ulta, guys, I'm so sorry. This should be the mass and here should be the density. Okay. Now once I get this, yes, NVIDIA, graphics card company. Yes, is it there in NCERT? No, it is not there directly in NCERT, but you can use it. Okay, it is not there in NCERT, but use it. You can get it by again modifying these drift speed formulas. If you modify these drift speed formulas now, you again get the same thing only. Okay, so you don't have to worry about the derivations, but just remember NVIDIA, graphics card company. Now, the mass which is there, mass can be written down as mass of each atom into the number of atoms. I can write it down as mass of each atom multiplied by the number of atoms, and this density will come over here. This n and this n cancels. What will be the mass of each atom? That will be nothing but your molar mass. This density is on the top only. Molar mass divided by Avogadro number. So hence this small n becomes Avogadro number multiplied by the density, whole thing divided by the molar mass. That's it. So this thing is not mentioned, but you know they are using it in NCERT. So that is why I am explaining this to you, how this came. Once you get this, small n can be easily found out as 6 into 10 to the power 23. Density is how much? 9 into 10 to the power 3. Molar mass, be very careful. It is grams, so 63.5 converted into kg by multiplying by 10 to the power minus 3. So that will be per mole. That's it. So I think you will get the answer from this. So whatever value of n you get right from here, so just substitute it over here. And that's how you finally get the drift speed. Is it clear? Yes. Okay. And this value comes out close to 1.1 millimeter per second. This value comes out close to 1.1 millimeter per second, guys. This is very small. Okay, as expected. Okay, don't expect the electrons to move with hundreds of meters per second. They will move very slowly, very slowly. But the electric field gets sets up instantly, speed of light. That is the reason when you turn on something, although the wire might be long, it's not like, sir, the electron is moving at millimeter per second, sir. It took 5 hours for the electron to reach the fan. So when I turned on the switch, sir, after 5 hours the fan turned on. No, it turns on instantly. Because the electric field reaches there and all the electrons in that wire are moving at a very slow speed. Everywhere it is moving instantly, but at a very low speed. Keep that in mind. And then there was the second part of question which talked about what is the speed of those electrons which are moving here and there. That is usually the thermal speed, which you will learn in thermodynamics of 11th standard. That is of the order of few hundreds of meters per second. There the Boltzmann constant comes. You don't have to remember it as such, this particular thing, but in thermodynamics you might have learned kinetic energy is equal to 3 by 2 kT. Temperature is given, Boltzmann constant is given, half mv square is equal to 3 by 2 kT. From that you can find that speed. Okay, but you should know it is, in the order of few hundred of meters per second. So these electrons move randomly few hundred of meters per second, but as they move randomly, they are moving ahead very slowly, 1.1 millimeter per second. So they move really fast like this, but they slowly drift like this. After few minutes, they slowly go here, they slowly go here. They are moving very fast, but their effective output is that they are moving slowly, drifting slowly at few millimeters per second. So that is why this question was even there, to compare three different speeds. The first one being the drift speed, which is in very small values. Then you have your actual speed of the electrons, which is decently large, and the final speed was your light speed, which is very, very large. I hope this is clear. Cool. Awesomeness, awesomeness, awesomeness. Let's go to the next thing. Let's go to the next example. In example 3.1, the electron drift speed is estimated to be only a few for the currents. How then is the current established almost instantly? This answer I gave you that time only. How come the fan turns on or the light turns on instantly even if the electrons move in very small speeds like millimeters per second? It's because the electric field sets up really quick. It asks all the electrons throughout the circuit to start moving. Everybody is moving slowly, but they are moving. That's very important. That's why current begins instantly. So that's the answer of the first question. I hope this is clear. Okay. Next, the electron drift arises due to force inside the conductor, but the force should cause acceleration. Why do the electrons acquire steady average speed? This part I explained over here. How is it that an electron does not continuously accelerate, rather it goes with constant speed? It's because of the collisions. It increases the speed, loses the speed because of the collision. So that is why it moves with a average speed called as the drift speed. So that is the answer for the second question. Okay, that is the answer for the second question. Clear, everyone? Next one. If the electron speed is so small and the electron charge is small, how can we still obtain large amounts of current in the conductor? Electron speed is small, electron charge is also small. How come the current is in amperes? The reason for that, there are too many such charges even in a small gram of a conductor. Even few grams is like an Avogadro number, which is 10 to the power 23 number. So the charge is small, that's okay. The speed is small, that's okay. But the number of those charges, huge. 10 raised to 22, 10 raised to 23. That's the reason why the currents are in few amperes or milliamperes. That's the answer for the third question. Clear, everyone? Okay, all right. When electrons drift in a metal from lower to higher voltage, does it mean that all free electrons of the metal are moving in the same direction? So when we say current is moving like this, is it true all the electrons are moving opposite to the current? No, all the electrons are not moving opposite to the current. Few of them might be moving even in the direction of the current, but they are very few in number. Majority of them, so maybe 1000 are moving opposite to the current. Maybe some 3 or 4 are moving in the direction of the current. So as a whole, if you take the effective number of electrons, they are moving opposite to the direction of the current. I hope this is clear. I'm so glad, Lucky. Thank you so much. And I'm so happy that I'm your favorite teacher. Means a lot. And I'm so glad you love physics because of me. Means a lot. Thank you so much. Are the paths of electrons straight lines between successive collisions with positive ions of the metal in the absence of electric field, presence of the electric field? So what about the paths? Okay, how are the paths going to be? Now usually the paths are going to be straight lines. Even though the positive charges are there, they will cause small deflections, but they are too negligible. But usually they are straight lines between one collision to the next collision. So they go like this, collide, go like this, collide, collide, collide. But due to the nucleus, there will be a very small deflection, but not so much and approximately straight lines. Okay, so all these same answers are written down over here in your NCERT as well. All right, let's go to mobility, guys. Let's complete this. Let's do the resistivity part also. Okay, all right, resistivity part also. Let's do this. Okay, now they have defined a new quantity called as mobility. Mobility means if I connect a battery, how fast are these electrons drifting? For the same battery, meaning a field is applied, if they are moving very quick, they are very mobile. If they are not, they are less mobile. So they defined it as drift speed by field. If their speed is large, that means their mobility is more. If I have to apply more electric field, that means I have to push them more. They are very lazy, so they are not so mobile. So mobility is less. That's the reason why mobility is defined as the drift velocity per unit field, electric field. Okay, per unit electric field. Drift speed formula we already know, it is E tau E by m. So if you substitute it over here, mobility will become just E tau by m. Okay, so mobility will just become E tau by m, because remember drift speed was E tau E by m. This E and this E can cancel out, and that's why you will just be left with this. So this can be also the formula, where T is the relaxation time or the average time of collisions. So this is something which you should know, which is given over here. This part, if you remember, I had explained it while explaining Ohm's law itself. Let me go back. Where is Ohm's law? Where is Ohm's law? Yes. I told you this law is only valid for conductors, which is basically ohmic devices. There are devices where voltage is not proportional to current. That is why they have mentioned about this, which is basically the limitation of Ohm's law. There are some deviations. Some materials do not obey proportionality. They have some non-proportional behavior. And such places, they are said to be non-ohmic devices. So very clearly mentioned over here, Ohm's law has been observed to be followed by many materials. There are devices where voltage and current are not proportional to each other. There do exist materials and devices where the proportionality does not hold. They are non-ohmic devices. Okay. This happens, for example, in a diode, which you will study in this chapter, chapter 14. That's basically semiconductors. So semiconductors are a good example of materials where Ohm's law is not obeyed. Okay, something which you should be aware of. They have shown how the current and voltages change. This is for a diode. You can see it's crazy, the voltage and current relationship. Then it is like this. It's very, very crazy. It is definitely not proportional. These are just graphs given. Then there is a material called as GaAs, gallium and arsenic. How does the current change with voltage? It's even more crazy. It goes up, then even comes down, again goes up. So you can see again non-proportional behavior. Okay, so they have just given examples. Please remember these graphs. They might just ask you which of the following graphs is the behavior of voltage versus current for GaAs. Some options will be given. If you know this graph, it is there in NCERT, you will immediately tick mark the correct option. Same thing for this. This you will learn in chapter 14, so don't worry, semiconductor chapter. Cool? Clear? All right? Great. Okay, so they have just mentioned what is Ohm's law where it is obeyed, and we'll be mainly studying those devices where Ohm's law is obeyed. Okay, that's fine. Now again they come back to resistivity of different materials. The materials classified as conductors, semiconductors and insulators are based on the resistivities. and of increasing values. So if you talk about conductors, which are basically metals, they have very low resistivity, obviously, in the range of this much, 10 to the power minus 8 to 10 to the power minus 6. Obviously, metals are conductors, so their resistances should be less. Resistivity also depends on the material, remember that. So they have very low resistivities, which kind of makes sense. Then you have other materials like what do you say, which are insulators like ceramics, rubber, wood, plastic, paper, etc. They will have very high resistances, something like 10 to the power 18 times greater than the metals. So it's much larger than the metals. In between both of them, you have basically semiconductors. They have decent resistivities, but the funny part is their resistances, change with temperature and also with what kind of materials are added in it. So we'll study that in the separate chapter. Don't break your head. How can resistance change by adding some amount of some impurity in it? That is called as doping. That doping you will study in chapter number 14. Don't worry about it right now. But it also depends on the temperature. Semiconductors like, silicon, germanium, their, resistivities also depend on the temperature and also something on the impurities, which is called as doping, which you will be studying later on. Now, how does it depend on the temperature is what we are going to study. How does it basically depend on the temperature? Now, usually, if you take a conductor, what happens is, when you basically heat it, what happens is these electrons which are there, which are going randomly, these electrons which are there, their thermal energy increases. So what happens is their collisions increases. Because of the collisions which are increasing, what will happen? They are colliding very frequently, guys. They are colliding very frequently. That means they will not have enough speed. Their relaxation time is less. Let's go back a little bit to see what happens. Let's see what happens, guys. Over here, maybe. Yeah. The time will be less. Oh, sorry. Where did it go? Here. Their time will be less. They will collide very frequently. So relaxation time will be less. What will happen to the conductivity? Conductivity will decrease. So resistance will increase. They will collide more frequently. Time will reduce. Less time between every collision. So conductivity will decrease. So resistivity will increase. Hence, you will basically notice that the resistance will increase. Is that clear? The resistance will increase. But for semiconductors, it is exactly opposite. Why it happens, we'll study that later on in that separate chapter. Don't have to break your head now. But remember, for semiconductors, it is different. How does it change for a conductor? That formula is given right over here. The resistivity is rho naught 1 plus alpha delta T, where rho T is the resistivity at some temperature. Rho naught is the resistivity at some reference temperature, let's say T naught, and alpha is basically called as the temperature coefficient of resistivity. This implies that when you plot the graph, it would be a straight line, and at temperatures much lower than 0 degrees, the graph however deviates. Okay, thus this can be used in approximate limited range. Okay, fine. Now from this, it should be clear that if on the horizontal axis you plot temperature, this is your temperature, this is your resistance, the graph should probably look like this. As you increase the temperature, the resistance will also increase. Makes sense. Usually the graph is not a straight line, it is a slight curve, but if you take a small range, it approximately looks like a straight line. So for a small decent range of temperatures, it is approximately a straight line. Otherwise, it is slightly curved. It is slightly non-linear. It is not a straight line, it is non-linear. So that is why for small ranges, the graph will be directly dependent on the temperature. So you can see temperature is there here, not t square or t cube or root of t. All those things are not there. Rather, only direct single power of time is there. That is what it is. Yes. I hope this is absolutely clear. Rho naught 1 plus alpha delta t. This equation is very, very similar to, if you remember, final length is initial length 1 plus alpha delta t. Where did you study this equation? If you have studied 11th standard physics, you will remember this was linear expansion of solids. You heat a solid, it will expand or contract. Exactly. So same kind of expression is even there for temperature, dependence on the resistance. So the resistivity at any temperature is resistivity at some reference, okay, into 1 plus some constant into the change in the temperature. This is called as your coefficient of thermal resistance. Like you had coefficient of linear expansion, alpha, beta, gamma. This is alpha, but for resistances. Exactly. Okay. I hope this is clear. Okay, I have reduced the thickness of the pen. Don't worry. I have reduced the thickness of the pen. Clear, everyone, till this point? So that is why this expression has come. And by the way, I have also mentioned over there also that it is approximately a straight line for a small range. Thus, this equation can be used as an approximately over a limited range of temperature around any reference temperature, whereas the graph is an approximately a straight line. And they have given that examples also. See this. Here they have given the example of copper, how the resistivity changes with temperature. You can see it is non-linear. But if you take a small range, it is straight line, another straight line. But big range, no. So from 20 to 30, yes. 20 to 50 also is okay. But 20 to 500, then I feel it's a problem because it's a huge range of temperature. You can see it's for decent temperatures. Whereas for nichrome, it is almost like a straight line. There are not many deviations. This is for semiconductor. This is very weird. Instead of increasing the resistance goes down. Why this happens? We will see it in that particular chapter, not here. But you should know that it is weird. Instead of increasing, it decreases. That's why there is a dedicated chapter only for that. Okay, great. Some materials, okay, magnitude and constant, these materials are thus widely used in wire, blah, 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 would change very little with temperatures, unlike metals, resistivity of some, okay. So this special example of nichrome is what you should know. Nichrome, you can see it is a constant line. It is almost like a straight line. Oops, what just happened? It's almost like a straight line. So Unlike copper or maybe aluminum where the graph is non-linear for a wide range, here it is a straight line. That is why they have clearly mentioned some materials like nichrome, okay, you can see there is hardly any dependence, very weak dependence with the temperature, and that is why they are usually used, they are widely used in wires, because how the temperature will affect the resistance. It's a linear relationship. Okay, this particular part, like I have been telling again and again, resistivity of semiconductor decreases with the temperature. This you will study later in chapter 14 of semiconductors. Don't worry about it right now. Okay, as we increase the temperature, I think this explanation I already gave. What happens? Okay, if you increase the temperature, collisions increase, relaxation time will go down, so conductivity will go down, and that's why resistivity will go up, because the number of collisions go up. That is something which I explained right over here, why the resistance increases. They have explained it right over here. So mentioning it here again. Okay, as we increase the temperature, the speed of the electrons, okay, increases, so frequent collisions, so the average time of collisions reduces. Okay, something which you should understand from this, which I have explained right over here, how heating it increases the temperature, increases the collisions, reduces the temperature, hence increases the resistance. That is what they have explained over here. Same thing again. Cool? Great. Okay. Well, this is fine. Okay. Now, this part, what they say is, N is not dependent on the temperature to any appreciable extent, hence the value of time plays a role, whereas for semiconductors N changes, and that's why you will see resistivity also depends on that. Okay, now if you notice this equation, the resistance not only depends on the time but also on the number of electrons which are free. But when you change the temperature, this N does not change. Meaning, if you take copper, if you heat it, don't expect more free electrons will come. Getting my point? If you take copper, aluminum, which are conductors, if you heat it, if you heat copper or aluminum or gold, don't expect there are suddenly more number of electrons. Already it has done enough. It won't give new free electrons. So that's why for conductors, you will see it is generally not dependent on N. But for semiconductor like devices, which you will again study later on, you will see this changes drastically. This changes drastically upon heating. N changes. So resistivity depends on N also. That is what they have mentioned. So again, an important point regarding conductors, N is not dependent on the temperature. In metals, basically conductors to any appreciable extent. And okay, but this is an exception now. This is an exception now for semiconductors. For insulators, semiconductors, N changes with temperature. N changes with temperature. We'll come to that again in chapter 14. Don't worry, we'll study that later on. Today only let's focus on conductors, and that is what they have also told somewhere over here. See, in most of these chapters, we will study currents in materials that obey Ohm's law. Very, very important, guys. We study currents in materials that obey Ohm's law, which means basically conductors. So except for that semiconductor chapter, everywhere else we study normal devices like conductors. So you increase the temperature, resistance increases, Ohm's law is obeyed, okay, everything is smooth. That is what they have told also clearly. Okay, there is a toaster which uses some wire. some small current passes and the resistance is found to be this much. When the toaster is connected to this supply and there is some new current, what is the temperature of the nichrome element? The temperature coefficient is also given to us. Read the question again and again, and let's see how do we solve this particular question. Okay. Now, here obviously resistance must be changing because you can see the current has changed. And because of that, I feel you should be able to use the formula for how resistance changes with temperature, and then you can find out what might be the new temperature. So, ready to solve this? Ready to solve this question? Usually our equation used to be resistivity is original resistivity 1 plus alpha delta T. But there is no harm in replacing resistivity with resistance, but then make sure here also you put resistance only. There is no harm in this. Now resistance is voltage by current. Voltage is I think the same. So voltage by the current at time t, voltage divided by original current 1 plus alpha delta T. Do you see that this voltage and this voltage just cancelled out and I get this equation? I think I know the current at time t, at some new temperature. What is the current? When a small current passes through it, the resistance is found to be this much. For this much supply, the current settles and, oh, I can't cancel the voltage, my bad guys. So sorry, because voltage only initially is given. My bad, sorry. What they have given is, at room temperature, the resistance is given. So R0 is given to me. At some new temperature, for that voltage, the new current is given. So voltage at some temperature and current at that temperature is given to me. This is my complete equation. Now it's just about substituting values. 230 volts, this much current is at that new temperature. So put 230 over here. Current is basically 2.68. Original resistance 75.3. 1 plus alpha is also given 1.7 10 to the power minus 4 into delta T. What is this delta T? Actually, final temperature minus original temperature, which is 27 degree Celsius. So from this you will get the temperature. The temperature comes out to be some 847 degrees Celsius. It comes out to be 847 degrees Celsius. Now if you look at the solution given in NCERT, you will get 100% confused. But if you look at my solution, it is very simple and elegant. I just said this is the resistivity formula. So resistance formula will also look similar. Old resistance already given. New resistance indirectly given because voltage and current is given. Oh, now I know this. I just need to find what is the new temperature. Got it? Everyone? Yes. I hope this is clear. Okay, let's go to the next question, maybe, or next concept. Okay, resistance of a wire is 5 ohms at steam point, at ice point is 5 ohms and at steam point is this much. When it is inserted in a hot bath, the resistance is this much. Calculate the temperature of the bath. Very interesting question, guys. Very interesting question. See, one thing we know, resistance for a decent range is going to be like a straight line for a decent range. Ice point means 0 degrees Celsius. Steam point means 100 degrees Celsius. At ice point, what is the resistance? 5 ohms. Steam point, what is the resistance? Where is it? 5.23 ohms. They have asked you now if the resistance somewhere is 5.795, that means it is much beyond than this, somewhere over here maybe, this is 5.795 ohms, then what is the temperature? Then what is the temperature? That is what they have asked. Is that absolutely clear what the question is? Now, one way to do the problem is using equations. One way of solving the problem is using equations. Other way is using straight line equation, but don't break your head on the straight line equation. Let's just use resistance at temperature T is original resistance 1 plus alpha delta T. Let's rearrange. RT by R0 is equal to 1 plus alpha delta T. Okay. So RT by R0 minus 1 is alpha delta T. Take R0 on the top, RT minus R0 divided by R0, bring that delta T below, is equal to alpha. Why did I write this? Because alpha is not given to me in the question. Alpha is not given to me in the question. That is the reason why I did this. Now, whether I do from here to here or from here to here, change the temperature from here to here or here to here, alpha should be the same. So for this part, the yellow part, final resistance would be 5.23. Original resistance was 5 ohms. Divide it with the change in the temperature, 0 to 100, the change is basically 100, multiplied by the original resistance. Original resistance was 5 ohm. That is for the yellow part. If you do it completely for that orange part, including right from here, final resistance is 5.795. Old resistance is 5 ohms. Whole thing divided by change in temperature. Change in temperature means T minus 0. So T minus 0. This is old resistance. Old resistance is 5 ohms. Do you see everything in this equation I know except for T? Solve this, I will get the value of temperature. Did you understand what we just did? Alpha was not given, so first I wrote down what alpha is. Then I wrote this equation 2 times, one here, but for different ranges. First for this and then for the whole thing. That's all. So from this, I get the value of temperature as 345.65. 345.65 degree centigrade. Clear how to solve this? Isn't this method much simpler? Isn't this method much simpler? Yes or no? Yes or no, guys? Correct? Very good. Great. So we will continue with this second part of the class in lecture number 2. Okay, so we have spent a good amount of time in 3.1 to 3.8 today. Okay, 3.9 onwards in lecture number 2. Okay, so I hope you will be marking your attendance quickly for lecture number 2 as soon as the session goes live. But till then, make sure quickly you have liked the session. Yes, and mention part 1 done, waiting for part number 2. Okay, see you very soon. We'll be completing electrical power, resistance in parallel series, batteries in parallel series, Wheatstone's bridge, etc. properly in detail. Okay, take care guys. Bye bye. Have a great time.